In my last podcast, I talked about the life of Evariste Galois and his contributions to abstract algebra. Between that podcast and my recent addiction to Rummikub, this thought process then led me, or distracted me, to thinking about number sets and groups. Mathematicians who've written about groups, mathematicians who have written about partition functions, and then about swimming and the current Olympic trials for swimming, which then conveniently led me back to abstract algebra, which was the topic of my last podcast on Evariste Galois. There is a connection here, I promise. The history of math is our intellectual foundation for understanding science. Science, beautiful, remarkable, awe-inspiring science. It's the creative foundation for our ineffable future. Hi, I'm Gabrielle Burchak, and this is my podcast, Math, Science, History. In the year 415, the infamous philosopher and mathematician Hypatia of Alexandria, Egypt, was savagely murdered by church monks. This murder shocked the Roman community and its government leaders. Hypatia was known far and wide as a respected philosopher, mathematician, government advisor, and a professor. Hypatia, The Sum of Her Life, is a book that I wrote that looks not just at the circumstances surrounding her death, but also at the sum of her entire life. I weave in the details of her education, disciples, Neoplatonic philosophies, female contemporaries, and the many mathematics that she wrote and taught about. There is truly more to Hypatia's life than her death. Hypatia, The Sum of Her Life, written by me, Gabrielle Burchak, is now on sale on Amazon. Buy your copy today. This week as I write this, the Olympic trials in swimming are streaming. It's exciting, and if you like watching the swimming trials, I'm sure like me, you are blown away by Hunter Armstrong's massive recovery from being last to finishing in second in the men's 100-meter backstroke final. Or watching Gabrielle Rose, who at the age of 46 and hasn't competed in the trials for 2 decades, absolutely own it in the water. She proved that age is just a number. Yes, it is. I love numbers. And so for those of you who watched the 2020 Tokyo Olympics, I want to do a call out to the medal winners Claire Curzan, Kate Douglas, Kate DeLoof, Paige Madden, Alex Walsh, Emma Wayant, and Andrew Wilson. And the reason why I named these specific swimmers is because each of these medalists worked with the mathematics professor Ken Ono, who teaches at the University of Virginia, is the STEM advisor to the provost, fellow of the Shannon Center for Advanced Studies, and a fellow podcaster with his own podcast called Who's in STEM? That's HOOS in STEM. So let's look at Emma Wayant's performance as a phenomenal swimmer. Before college, she could swim the 500 freestyle in 4 minutes and 38 seconds. By the time she competed in the 2022 National Collegiate Athletic Association Swimming Championship, her time was at 4 minutes and 34 seconds. This was due to her adjustment when her flip turns managed to gain up to 0.3 of a second per turn. This made a significant difference in her speed. Ono's process of analyzing the swimmers included sticking small sensors on the backs of the athletes to analyze when they sped up and when they slowed down. In an interview with NPR, Ono stated that, quote, "No two people have the same body type. And there are so many different factors that have to come together to make a world-class swimmer," unquote. And that is so true. So as he and his assistant began to analyze each swimmer as a math problem, they used the sensors on their backs as well as sensors within the pool to see when and how an athlete would generate force and the areas where they are inefficient. It also allowed them to see the depth of the dives and the angles that they pushed off a wall, as well as the distance between their feet when they set up their push. They analyzed every minute movement of every swimmer to optimize each swimmer's race. Clearly, this process worked because in March, Virginia's women's swimming and diving program won its 4th consecutive NCAA Division I Women's Swimming and Diving Championship title. So, what does all this information have to do with Evariste Galois? Well, in my last podcast, I briefly talked about Galois groups. Galois groups are used as symmetry groups. Within these groups, he analyzed the symmetries and permutations of the roots. Taking this a bit further in the context of symmetry and group actions, one can use integer partitions to study the structures of these groups. And so I'm going to break this down a little bit. First, I'm going to address Galois groups, and then I will address Galois groups used as symmetry groups, and then I will talk about integer partitions and how they are used to study the structures of these groups. One thing mathematicians have in common is that we love puzzles, and mathematics are puzzles. And in algebra, some puzzles are simple, like x squared equals 4. And when you solve that equation, you find that x equals 2 or negative 2. But when we have a puzzle that's more complex, like x cubed minus 13x squared minus 36, solving it can get a little tricky. This is where we call in the Galois groups. Galois groups are kind of like the secret informers or operatives or qualified representatives of mathematics that work behind the scenes to solve the mysteries of the equations. And what's cool about these representatives is that they can help us by showing us if a puzzle can be solved with basic operations like addition and multiplication, or by taking the roots of the equation like the square roots or the cube roots. And when we go back to our complex puzzle, the Galois groups can shuffle around the solution of the equation without changing the equation itself. As a result, the equation x cubed minus 13x squared minus 36 can be factored into x squared minus 9 times x squared plus 4. This gives us the roots x equals 3, x equals negative 3, x equals 2i, and x equals negative 2i. I represents an imaginary number, so it would be x equals an imaginary number of 2, and x equals an imaginary number of negative 2. The splitting field of this polynomial over the set of all rational numbers is a set of all rational numbers that also includes 3 and 2i, which is like a bigger set of numbers that includes all the usual fractions and whole numbers, plus any number you can get by multiplying or adding 3 and 2i together in any way. It is a way to create a new number, which includes real numbers like 3 and imaginary numbers like 2i. And so, the set of all rational numbers with the numbers 3 and 2i is a degree for extension of the set of all rational numbers. Since the polynomial x cubed minus 13x squared minus 36 is separable, which means it has distinct roots and its splitting field is a degree for extension. The Galois group will be a subgroup of the symmetric group S sub 4. Yeah, that was a mouthful, and I'm sorry. This is a podcast for everybody, not just mathematicians, so I'm going to explain it further using my favorite game, Rummikub. Let's imagine you're working on a tabletop puzzle, and you've solved the puzzle, and then your friends come over and they decide to rearrange the pieces of the puzzle. No matter how they arrange it, the picture on the puzzle remains the same. And when you ask them how they did that, they can tell you exactly how they did it so that you can do it again and again. They've given you the rules. Now, let's imagine that you have that same puzzle, and your friends come over and start to rearrange the puzzle, but it doesn't look the same as when they started. And so, rightfully so, you're probably like, hey man, put it back. And they're like, hey man, we can't. You're going to have to find the rule book. So where do you find that rule book? Well, I'll come back to that question. Now, let's talk about how Galois groups can be used as symmetry groups. Let's take the same puzzle analogy. Instead, this puzzle includes squares of different colors. And as usual, your friends barge in and they decide to shuffle the squares. They flip them, they turn them, and they put them back in the puzzle, and voila, the puzzle looks exactly the same. This is called symmetry. Now I'm going to move on to integer partitions and how they are used to study these Galois groups and symmetry. As I noted in my intro, I've become very addicted to the game Rummikub. I'm fascinated with this game and how it applies to Galois groups and integer partitions. If you are not familiar with the game Rummikub, it is a tile-based game that combines the elements of rummy and mahjong. The goal is to be the first player to play all your tiles by forming sets and runs on the table. In the beginning, each player pulls 14 tiles from the bag. The bag originally holds 106 tiles. All the tiles are numbered from 1 to 13, and there are 4 colors for 2 sets each, and 2 jokers. So, when you lay them all out in order, there are 2 runs that go from 1 to 13 in red, 2 runs in blue, 2 runs in black, and 2 runs in orange, or whatever 4 colors the makers of the game decide to use. And then you have your 2 jokers. Kind of like the 2 jokers that keep coming in and messing up your puzzles. So, when you play, you lay out your first turn, which is called the initial meld. It has to be worth 30 points. It can be 3 10s, 3 11s, or 3 12s of different colors, or a single color run of numbers that equal the number 30, like 1, 2, 3, 4, 5, 6, 7, 8, all in the color red. So after you play your first meld or melds that total 30, you can continue with the game on your next turn. As you continue to play the game, you can rearrange the tiles and add your tiles to existing melds to create new ones. When you're all done playing your tiles and you have no more, you're the first one to get rid of all your tiles, you have won the game of Rummikub. In this analogy, integer partitions are represented by the possible plays that you can make with your tiles. You could have an integer partition of a run like 6 red tiles numbered 1 through 6, or another integer partition that could be 4 tiles of 12 in different colors. As a result, integer partitions help us to see all the possible plays that we can make with our solutions. In other words, an integer partition helps us to see the equation assembled in ways that we wouldn't be able to see before if we just dumped all the tiles out on the table. And much like how the sets of the tiles help us to understand the structure and the symmetry of the groups that we play, integer partitions do the same thing for equations. In this analogy, integer partitions are like the sets in the game. In mathematical terms, integer partitions show all the different ways that you can combine solutions that add up to the value of the original equation. And how does all this tie back to swimming? Well, Professor Ono and Professor Dr. Jean Brunier of Germany's Technical University of Darmstadt published a joint work titled An Algebraic Formula for the Partition Function, wherein they found a finite algebraic formula for computing partition numbers. I will provide a link to that paper at my website, mathsciencehistory.com. Oh, hey, and while you're there, please feel free to click on that large coffee button and buy me a cup of coffee, because every cup of coffee that you buy provides funding for this podcast. So, back to the paper. In simple terms, Professors Ono and Brunier solved a complex number puzzle, and in a sense, they wrote the guidebook, the rule book to this number puzzle. Ono has done extensive work with partition functions. So, what he did was apply his method to a famous number problem called the partition function, which in simple terms is a function that finds different ways to add up numbers to reach a certain total. So, to go back to our Rummikub analogy, let's say you have tiles numbered from 1 to 4, and you want to create groups of tiles where the sum of the numbers is always 4. Here are the ways that you can do it. You can use the number 4 tile by itself. You can combine the number 3 tile and the number 1 tile. You can pair up 2 number 2 tiles. You can combine the number 2 tile, the number 1 tile, and another number 1 tile. Or you can use 4 number 1 tiles together. If you had a rule book for Rummikub, it would tell you that for the number 4, there are 5 possible groups, because I just listed 5 possible ways. In essence, Professor Ono found brand new patterns and connections in the world of numbers, and his work on partition functions are like that rule book that helps you find all the possible group combinations to win the game of Rummikub, or to put the puzzle back together again that your friends messed up. And so there you have the connection between Evariste Galois, abstract algebra, Rummikub, and swimming. Welcome to the rabbit hole that is my brain. And with that being said, my solar heated pool is up to 87 degrees. So I'm going for a swim. And until next time, carpe diem. Thank you for joining me at Math Science History. Please remember to subscribe to the show. Also, if you could please leave a rating or a review, it would be really appreciated. Because those ratings and reviews really do help to increase my listenership, which help to get me more sponsors, which help me keep the podcast up and running. If you want to learn more about the history of math and science, please visit me at mathsciencehistory.com. If you like what you're listening to, and if you like what you're reading, please feel free to click on that coffee button and buy me a cup of coffee. Every cup of coffee that you buy helps me pay for the expenses that go into making this podcast. Also, if you're interested in leaving me a comment or chatting with me, you can always find me on your preferred social media platform, including X, Instagram, Facebook, LinkedIn, Goodreads, TikTok, Threads, etc., etc., etc. Just go to Google and search for Gabrielle Burchak. You can find me everywhere. Until next time, carpe diem.